Hello everyone, good afternoon to all of you. Welcome back to Inorganic Chemistry class. Today's lecture is focused on group 13 elements, that is the boron family. Okay, so in the earlier lectures we have given you a insight on group first alkali metal chemistry and alkaline earth metal chemistry. Now today we are entitled to give you a brief outlook on the chemistry of boron family, right? So once we talk of boron family, this family constitutes, that is boron, aluminum, gallium, indium and thulium. So these are the five elements which are actually found in a boron family, right? So this this class of uh, elements actually uh, comprise, that is boron and aluminum and gallium and indium, and the atomic number of these elements are 5 for boron, 13 for aluminum and 31 for gallium and 49 for indium and 81 for thulium, right? So on the basis of electronic configuration, we can find a diverse class of physical and chemical properties among these elements, right? So first we will consider these elements and where it is found and what are the natural abundancy of these elements. So once we talk about the natural abundancy of these elements, so first thing is that boron. So boron is generally is least abundant elements in this group, and most important natural abundancy of this boron family is aluminum, right? So aluminum is found in a major quantity in the earth crust, and rest of the elements, that is gallium, indium and thulium, so they are actually rare elements, so they have very low natural abundancy, right? So these are the actually abundance of the elements of the boron family. So once we uh, actually talk the chemistry of this class of family, then first we will consider the electronic configuration of this family, right? So electronic configuration of this group is like that. So here boron have atomic number 5. So this is very close to the next noble metal, that is helium, which has a atomic number of 2, right? So this is the electronic configuration. Next electronic configuration, that is 2s2 and 2p1. So and the last electron of this boron enters into the p subshell, right? So this is p subshell. So because of the presence of last electron in p subshell, so all these elements, so they are called p block elements, right? So because here 2s2 2p1, right? And for the aluminum, the outermost configuration is 3s2 3p1, okay? And for gallium, that is 3d10 4s2 and 4p1. And similarly for indium, the outermost configuration is 4d10 5s2 5p1. And for thallium, that is 6s2 6p1. So what you are observing here, all these elements after a electronic configuration, you will have ns2 np1, right? So ns2 np1 type of electronic configuration means here the electrons are found in s orbital as well as in the p orbital of the valence shell. So valence shell actually is because of the coupled effect of these two orbital, that is s and p orbitals. Okay, so total number of these two orbitals contain total number of these two orbital contains 3 electron, right? It means all of these elements actually possess 3 valence electron. Okay, in the valence state, so what you are observing here, that is principal quantum numbers. So for the first element, that is boron, the principal quantum number is 2, right, in the valence state. So here n is equal to 2. It means it is located in period 2 of the periodic table. So periodic table of period 2 contains boron, and similarly n is equal to 3 for aluminium. It means in the periodic table, in the third period, the aluminium is located, right? So similarly, in the fourth period, gallium located, and in the fifth period, so this is indium, and in the sixth period, that is thulium, right? So these elements actually are placed in periodic tables with a period number 2, 3, 4, 5 and 6. Fine. So the periods actually they are guided by the principal quantum numbers. Fine. Now how these elements they are kept in the group 13s, right? So as you are seeing here that all these elements have valence electrons, that is 3, right? So 3 valence electrons means so they are kept in the group 3rd, right? So in the modern periodic table, group 3rd are replaced as group 13 elements. Okay, so the main group chemistry comprises that is group 1st alkali metals, and group 2 that is alkaline earth metal. And apart from these two main groups, the next group is that is group number 13s, and they are actually located right side of the periodic tables. Okay, so whenever you have seen the periodic tables, so you have seen that the group 1st and group 2nd elements they are placed in the left side of the periodic table, and in the middle, so there is a transition elements, lanthanide elements, right? And in the right side of the periodic table, all the elements, so they are actually p block elements, because the outermost electrons enter into the p block or p subshell. So the right side of the periodic table so are actually suitable for the all the elements having p subcells, right? So this class of elements have p subcell in the outermost configuration as you have, right? So 2s2 2p1, 3s2 3p1 and 3d10 that is completely filled, right? So 4d10 that is completely filled, and 4f14 it is also completely filled. Here in the last element, that is F and D subcell both are present in intervening as a intervening subcells. Here d orbitals are present, here also d orbital presents, right? So the physical and chemical properties, they are related to the their valence electrons and its reactivity. Okay, now what is the valency? So valency is 3. All the elements actually possess a valency of the 3. Okay, so because of the presence of total number of electron in the outermost shell, that is 3, so they are actually 3 valence electrons. Fine. Now from the electronic configurations, you also dictate that they are all kept in group 30. Group 13. And group 13 is known as boron family. And the head of this family is boron. Right? So this is boron. And the last member or tail of this class is thallium. Okay. So boron is the lightest element of this group. However, the thallium is the heaviest element of this family. Right? So in the group 13 and periodicity, that is 2, 3, 4, 5, 6. So they are kept. And all these elements, they are called representative elements. Right? Representative elements. So because they have two subcells, that is S subcells and P subcells. So both contains electrons. So that is why they are representative elements. Nice. Now the boron, so that is actually non-metal. However, helium and aluminium. So aluminium and gallium, and aluminium is the most important metal, right? So it is metal. Boron is non-metal or semi-metal. Gallium onwards, gallium, indium and thallium, so they have a property similar to the metals. So they are all metallic in characters, right? But in the previous lectures, we have taught you about the physical and chemical properties of group first alkali metals and group 2 alkaline earth metals. So as you know that from moving left to right in the period, the size of the elements decreases. Fine. Because effective nuclear charge is increased in the respective period. Okay. But once moving down from top to bottom, what you have observed, the size of the elements actually getting increased. So because of increase of the principal quantum number at every stage. So in case of boron, the principal quantum number is 2, and that is for aluminium 3, and for gallium 4, and for indium that is 5, and for thallium that is 6. So the valence orbitals, so they are very far apart from the nucleus. It means they have increased size across the group, right? Now once we talk on covalent radius, right? So covalent radius, it is defined as if we have two type of element, that is AB, then covalent radius will be the distance between these two centers divided by 2 is called covalent radius, right? So the covalent radius of these group elements, that is for boron. So boron has 80 picometer, so that is actually picometer. So covalent radius of boron is 80 picometer, right? So in case of that is thulium, it is 155, right? And continuously it is getting increased, right? So here that is 125, and here also 125. In case of aluminum and gallium, so the covalent radii are similar. It means they have similar physical and chemical properties. So that is why they have exactly equals covalent radii, right? Now, metallic properties, metallic characteristics. So because of presence of valence electron in the outermost configuration, so they show metallic properties, and it have a metal-metal bond. So because of the lattice structure, so metallic radius, boron, since it is a non-metal, so it has no experimentally determined metallic radius. So it is remain as such. For aluminum, this is 143 picometer, and for gallium it is 141, for indium it is 166, and for thulium it is 177. So metallic radius, that is increases, right, irregularly. For aluminum that is 143, and for gallium it is 141. So 2 picometer is less, and again it is increasing for indium 166 picometer, for 171 picometer. So that can be illustrated very well, and in the I will discuss about how this variation occurs. But ionic radius ki baat, if you talk on the ionic radius, it means all the elements, suppose M is stands for element, they all exist as M3 plus, right? So if you talk on the ionic radius, it means the smallest size, that is cation B3 plus, which is unstable still. So it has ionic radius that is 27 picometer, right? And the last member of this group, that is thulium, has largest ionic radius, that is 89 picometers. So as you can see from this table and from this these data, the first member, the head element, that is boron, has lowest ionic radius. It means it has very less tendency to form B3 plus or M3 plus like structure. However, rest of the elements, from moving top to bottoms, what you observe, the ionic radius actually getting increased, right? The highest ionic radius, so the biggest ionic radius for thallium 89. It means thallium is actually behaves like a metal. So it has ionic radius 89. So it can be easily converted into M3 plus. So the general oxidation state of all these elements exist as M3 plus. So 3 electrons getting oxidized from the outermost valence electrons. So as you have seen that they all have ns2 and p1 configuration, right? So these three electrons, they are removed to form m3 plus, right? So trivalent, and they have a common oxidation state, that is 3. So all these elements from boron to thallium, they possess oxidation state, that is +3, right? But the +3 oxidation state, so they are not increases the stability of all these elements. Rather, some elements of this group exist as +1 oxidation state. Okay. So what you are seeing that the boron, aluminum, gallium, indium, and thulium in general they have +3 oxidation state. Okay, but this aluminum is the most important metal, so they have +3 oxidation state. Indium and thulium, right? So most important point, it should be noted. Indium and thulium, it has 80 and 89 picometers ionic radius, right? So these two elements possess +1 oxidation number rather than +3 oxidation as it is expected, right? So in general all these elements exhibit +3 oxidation state, but the +3 oxidation state decreases from top to bottom. However, +1 oxidation state increases from top to bottom. So this is because of the inert pair effect. And what is inert pair effect? So that will be illustrated. So this is your boron, this is your aluminum, this is your gallium, and this is your indium, and this is your thulium, right? So here 2s2, 2p1. Here 4d10, here 4f14, 4d10, that is 5d10. So this is the electronic configuration, what can be 4f14. So in case of thulium, that is 4f14, 5d10, and 6s2, 6p1, right? So what happens here in the intervening cells, there is a presence of F and D subcell, and in case of indium, here D subcell. And you know that Z effective, that is Z effective is equal to Z minus sigma. This is Slater's rule. Effective nuclear charge on an element will be the nuclear charge, that is equivalent to atomic number, minus this is shielding constant or screening coefficient, right? Yes, is shielding constant. So larger the value of sigma, lower will be Z effective, right? And if sigma is low, then Z effective will be high. From this equation, this can be elucidated. So depending on the value of, that is, screening constant or shielding constant, we can predict the effective nuclear charge on any elements. But in case of indium and thulium, so here that is 4F14, 5D10, that is 6S2 and 6P1. Here that is 4D10, 5S2 and 5P1. The intervening subcells here, D subcell here, D and F, both subcells are present. So as you know that D and F subcells that are present in inner cell configurations, they have poor shielding constants, right? So they poorly shield the valence electrons, right? So valence electrons means we have ns2 and p1, that is valence state. And because of presence of that is F and D subcells, so they have electrons that is completely filled, so they have poor tendency to shield this 6s2, so poorly sealed. It means the pair of electron, that is s2, so pair of electron getting attracted towards nucleus, so it is strongly attracted towards nucleus. So because of poor shielding constant of the D and F subcell, the contribution of the shielding constant or screening constant is very low for F subcell and D subcells. So the low value sigma indicates for these two elements the Z effective will be very high, and if there is a very high Z effective nuclear charge, it means the pair of electron in the s subcell or s orbital, so they remain inert, right? So what is inert pair effect? Inert pair effect. What is inert pair effect? Inert, so they are inactive pair of electron, and effect is the phenomena. So inert pair effect is a phenomena in which a pair of electron that is present in the valence s subcells, they remain inert. So because of the poor shielding constant of the penultimate F and D subcell or F and D orbitals. So the sigma is very low for thulium, and that is for indium it is comparatively little larger. So because here two penultimate subcells, that is F and D, here only one, that is D subcell. So here sigma will be very low, right? So Z effective will be high, and higher the Z effective, it means the valence S state or S2 pair of electron that is strongly bounded to the nucleus. So nucleus has a positive environment, so they strongly attract the electrons which are present in the valence s orbitals, so they remain inert. So only the electrons so that is removed here is from p orbitals, that is p1, and here also that is p1. So only one electron from this system can be removed. So indium can be converted into indium plus 1 by removing one electron, and that is thallium, that is Tl. So this is Tl. It is getting Tl plus electron. So these two elements, because of inert paired effect, they actually possess +1 oxidation state, right? So +1 oxidation state for indium and thulium. So once we move from top to bottom, the stability of the +1 oxidation state increases because of the inert paired effect, and stability of the +3 oxidation state decreases, right? So the boron is the smallest element, so they have very weak tendency or poor tendency to form B3 plus, right? So because of the anomalous characteristics. But boron onwards, that is aluminum and gallium, they have very good oxidation number, that is +3 oxidation state, but rest of these two elements have +1 oxidation state. So oxidation state regularly, it is not common for all these elements. So what is the effect of inert pair effect? So inert pair effect, actually what happens here, inert pair effect, and because of the inert pair effect, the S2, a pair of electrons which are present in the valence state, does not take part in chemical bond formation. So they have very low tendency to participate in a chemical bond formation. So only the chemical bond formation will be through the contribution of the p orbitals or p electrons, right? So this is the beauty of inert pair effect. Now in case of boron, right? So boron is the smallest element, right? And it is the actually non-metal. So once you talk about the electronegativity of these elements, now electronegativity of these elements, so that may vary according to this is chi, that is electronegativity. So the first head group of boron family, that is boron, have that is highest electronegativity 2.0. But in the previous lectures, what you have studied, the electronegativity in case of group first alkali metals and group second alkaline earth metals, so they have lower electronegativity compared to the boron family. So larger the electronegativity, so greater will be covalency or covalent character of the compounds which are formed through the these elements. So boron have 2, that is electronegativity, so it forms a covalent compound, right? And this thallium, it has also electronegativity that is similar to the boron, so it also form covalent compound, right? But because of presence of +1 oxidation state, so they also form ionic compounds, right? So because these two elements have +1 oxidation state, right? So they form ionic compounds because of high metallic characters of these two elements, right? And rest of these elements, they actually have 1.6, 1.8 and 1.8 electronegativity. So all these elements, they favors covalent bond through the other elements, right? And once you talk standard electrode potential, that is inert voltage, right? So all these elements, they actually possess negative standard electrode potential, right? So only thallium possesses positive standard electrode potential, that is plus 0.72 volt. So this confirms that this thallium is inert, or it is not highly reactive compared to rest of the other elements of the same family, that is boron, and most important, that is aluminum 1.68. So it has very large negative standard reduction potential, and this confirms that so it has a larger reactivity compared to the other elements. That is why aluminum actually react with oxygen at room temperature to form aluminum oxide, that is Al2O3. And the surface of the aluminum, so they are actually passivated with the layer of aluminum oxide. So it shows that aluminum is highly reactive because of negative standard reduction potential. But once you talk on gallium, so that is also uh, possessing, that is negative standard reduction potential. So it is also reactive compared to the aluminum, and indium has less negative, that is minus 0.34. So indium is next less reactive element of this class or this family, but most reactive, that is aluminum. So aluminum actually in powder state, so they possess high reflectivity, or it has high reflectance. So once it is mixed with a silver color paint, right? Silver colored paint, that is Ag colored paint. So they reflect the most intense color and shining because of the high reflectivity of the aluminum in powder state. Okay, and most of the elements of this family actually they uh, behaves, their compound behaves as a most important industrial catalyst for the synthesis of organic compounds and for the development of new materials for the industrial purpose and applications. Okay, so in case of once you think on the melting point of these elements, so boron, which have 2300, so that is very high melting point. So it confirms that boron is very hard, tough, right? So and the most important is that here the lowest melting point for gallium, that is 30 degree centigrade, right? So because gallium has low metal bonding or low metallic characteristics, so it has very low melting point, and that confirms that gallium actually exists as liquid at room temperature because it melts easily at 30 degree centigrade. So gallium is the elements which are found at room temperature at liquid state, right? And next, that is indium. Indium has melting point 157, and the most important, that is thallium. So it has 304 degree centigrade. So the most hard and tough element of boron family is boron, right? That is the head of the that is boron family, and rest of the elements have little lower melting point, so that actually confirms because the formation of the covalent bond. So all these elements actually forms covalent bonds, and the compounds having covalent characters, they actually exhibit lower melting points, right? So in case of, that is here, now in case of compounds, so that is actually boron. Boron has high reactivity. It react with oxygen at room temperature. It forms B2O3. That is boron trioxide, which is acidic in nature. Acidic in nature. So once you talk electronic configuration for boron, that is 2s2 and 2p1. So this is the balance state, and the ground state electronic configuration for this is S and this is P subshell. So here 2 electrons are present in the S subshell. So this S orbital, 2s orbital, that is 2p orbital, contains 2 electrons which are oppositely oriented, and finally p subshell contains single electron. So here 2 orbitals are vacant, right? So that can accommodate, and 2 electrons in the S subshell, they are in paired state, so it can't form covalent bond. So here it is expected, so because of presence of 1 electrons, that can form single covalent bond. Single covalent bond. But formation of single covalent bond does not provide saturation. So what happens, once the ground state is excited through the energy, then this is excited state. So ultimately the electrons which are present in the S subshell, they get excited and promoted towards, that is in the p next p orbitals, that is a 2p orbitals. So now here 3 single electrons are actually available in the excited state. So what you can expect here, 3 covalent bond can form through the share of 3 single electrons by other elements. Suppose we have that is in case of boron, that is BF3, that is boron trifluoride. So boron, it can bond 3 bond with fluorine. So 3 bonds means sp2. So this boron actually comprised sp2 hybrid orbitals, right? So hybrid orbitals means it has trigonal shape. So this boron trifluoride has triangular, you can say simply triangular geometry, right? But these 3 bonds total makes a contribution of 6 electron, right? So 6 electrons actually present in the balance state, which is 2 unit less than the complete octet. So this class of elements actually develops incomplete octet compounds. So incomplete octet compounds. Incomplete octet compounds. And because of the deficiency of 2 electrons, so and availability of vacant next p orbital, so this class of compounds actually electron deficient and act as a Lewis acids. So Lewis acid means it has tendency to accept a pair of electron. So this is the available orbital which are present in the valence state. So they can accommodate a pair of electron through the coordination bond. So now it ultimately that is saturated or stabilized by 4 bonds to form a complete octet configuration. So all the compounds of this class actually they form electron deficient compounds and they are Lewis acids. So Lewis acids means they have tendency to accept a pair of electron from the donor or Lewis base. So most of the compounds they are acidic. So suppose we have halide compounds. In case of BX3, that is BF3, BCl3, BBr3 and BI3. So this is trifluorides and this is triiodides. What you expect the acidity order or Lewis acidity order. So here you can think that the fluorine is the most electronegative element. So naturally this fluorine, so because of the high electronegativity, it can attract its shared pair of electron. So this will ultimately delta negative and this is delta positive. But because of presence of p electrons, so ultimately it is overlapping with the backend p orbitals. So it has tendency to form p pi back bonding. So that is what described as back bonding. So here unsaturation or deficiency is stabilized. So you can't expect that BF3 is most Lewis acid. Rather, in case of BI3, so naturally iodine is larger. So here overlapping of p orbitals on the boron and p orbitals of the iodine, they are not actually superimposed to each other. So there is a deficiency is still maintained. So if there is a high deficiency of the electrons in the backend p orbitals, so they will be highly acidic in nature. So the order of the Lewis acidity in case of this trihalides, that is Bi3 and BBr3 and BCl3 and now BF3. So BF3 is least acidic and it means this is very low Lewis acidic characteristics and compared to this boron triiodide. So boron triiodide has very high Lewis acidic characteristics. Okay, so these are the actually parameters on which we can actually classify the various physical and chemical properties and its reactivity. And the most important thing is that is in case of boron family, we have that is NaBH4 and lithium, aluminum hydride, and that is lithium H. So these all compounds actually possess boron atoms. So that is sodium borohydride and lithium aluminum hydride and lithium hydride. All these compounds actually they are very good donor of hydride anion. So they are acting as a reducing agent in many organic synthesis. So they are hydride donors. Right, and they are very good reducing agent for organic transformation. So this is the beauty of boron family and the elements which are present in this class. So here it is because of boron, here it is because of aluminum, and this is similar to the lithium hydrides which possess Li plus and H minus. So they are all hydride ion donors. So this is the actually chemistry and its properties, so that can be correlated with various reaction that forms. uh, Here we have a very good example of boron compounds, that is boric acid, BOH ka whole thrice. So when it is heated, right, so it forms B2O3, that is boron trioxide, which is acidic, plus it is dehydrated. It means water is going to be removed from the structure, right? So once the water is dehydrated from the structure, so it is getting a most important oxide materials, that is boron trioxide. So there have a diverse class of uh, chemistry depending on the chemical and general electronic configuration, so that can be understood through proper uh, proper correlation of the physical parameters. Okay, so one last point is the of this family is density, right? So this is last point actually. Now what you expect for density? Boron, aluminum, gallium, indium, thulium. Density means, so that is mass upon volume. So all the elements are spherical in nature. So all the spheres have 4 by 3 pi r cube, that is volume. So if the radius is small, then there will be high volume and accordingly low density. But in the respective group, what you observe here, either covalent radius or metallic radius or ionic radius, naturally the radius is increasing in the group. Radius increasing means it has that is very high volume, so low density. So in the group, density decreases. So this is density decreases, and the most denser element, that is boron, which is also conferred because of high melting points, and the that is uh, rest of the other elements, so they have a lower density because of the formation of the covalent bonds. So these are the actually chemistry, and that will help to understand the p block chemistry or boron family. Okay, so thank you students for listening and watching this scientific lectures, which will help you to design accordingly. ओके, थैंक यू। हो गया? साक्षी जी उसको बंद करिए, है ना? उसको बंद कर दीजिए। अरे नहीं बंद कर पाते हो। So that is, ये क्यों नहीं खसक रहा है भाई? ओ, स्टॉप रिकॉर्डिंग।